When designing a grounding system for a light industrial facility approximately 160 by 250 feet with electric rooms in 3 corners, each containing a step-down transformer from 480 volts to 120/208 volts, several grounding options exist. The original plan involved a ground ring around the building with ground rods placed periodically, and the main panel's grounding electrode conductor and the grounding electrode conductors for each separately derived system connected to this ring in 2 places. While this provides an adequate grounding electrode system, it may be considered overkill by some. Firstly, it is possible to use 2 ground rods outside each of the 3 electric rooms as the grounding electrode system. This approach is acceptable if the ground rods meet the requirements outlined in National Electrical Code Section 250.52 AFRI. However, it is not necessarily the optimal or most cost-effective solution. Secondly, it is essential to bond the ground bars in all 3 electric rooms together. National Electrical Code Section 250.50 mandates that all grounding electrodes of a building or structure must be interconnected to form a common grounding electrode system. This interconnection ensures that all equipment within the building is properly grounded and protected from electrical faults. The common grounding electrode system minimizes voltage differences between different parts of the electrical system, thereby reducing the risk of electrical shock and equipment damage. Thirdly, running bonding conductors overhead across the building is permissible, using bare copper inside polyvinyl chloride conduit for physical protection. National Electrical Code Section 250.66c allows the use of bare copper conductors as grounding electrodes, provided they are adequately protected from physical damage. Enclosing the bare copper conductors within polyvinyl chloride conduit provides the necessary physical protection, preventing accidental contact and potential damage to the conductors. Fourthly, regarding the cost difference between the original ground ring plan and the downsized plan involving ground rods only, the ground ring system generally incurs a higher installation cost. This is attributed to the increased material requirements, such as additional copper conductor, and the greater labor effort required for installation. However, the cost difference is not likely to be significant, especially for a building of this size. The overall cost depends on factors such as local labor rates, material prices, and the specific site conditions. Therefore, considering the factors outlined above, it is generally recommended to install 2 ground rods outside each of the 3 electric rooms, ensuring compliance with National Electrical Code Section 250.52 AFRI. Furthermore, interconnect the ground bars in the 3 electric rooms using bare copper conductors inside polyvinyl chloride conduit for physical protection. This approach provides a safe and effective grounding system for the building while minimizing the installation cost. The specific requirements for grounding electrode systems are detailed in Article 250 of the National Electrical Code. It is critical to adhere to these requirements to ensure electrical safety and system reliability. Grounding electrode systems provide a low impedance path for fault currents to return to the source, facilitating the operation of overcurrent protective devices such as circuit breakers and fuses. Without a properly installed grounding electrode system, fault currents may not be cleared quickly, leading to equipment damage, fire hazards, and electrical shock. The size of the grounding electrode conductor is determined by National Electrical Code Table 250.66, which bases the conductor size on the size of the service entrance conductors or the equivalent for separately derived systems. The grounding electrode conductor connects the grounding electrode system to the equipment grounding system at the service equipment or the separately derived system. The equipment grounding system, which is distinct from the grounding electrode system, provides a path for fault currents to return to the source from non-current carrying metal parts of electrical equipment. This is achieved by bonding together all metal enclosures, raceways, and equipment frames. The equipment grounding conductor is typically run with the circuit conductors and connected to the grounding terminal at each outlet and equipment location. In the case of separately derived systems such as transformers, the grounding electrode conductor is connected from the transformer's neutral point or grounded conductor to the grounding electrode system. This connection ensures that the separately derived system is properly grounded and that fault currents can flow back to the transformer, causing the overcurrent protective device to trip. When installing ground rods, it is important to drive them deep enough into the earth to reach a low-resistance soil. The National Electrical Code requires that ground rods be at least 8 feet in length and driven so that at least 8 feet is in contact with the soil. If rock bottom is encountered, the ground rod can be buried horizontally in a trench at least 30 inches deep. The spacing between ground rods is also important. The National Electrical Code recommends that ground rods be spaced at least 6 feet apart. This spacing helps to reduce the overlap of their effective grounding zones and improves the overall effectiveness of the grounding system. When connecting the grounding electrode conductor to the ground rods, it is important to use listed connectors suitable for direct burial. These connectors are designed to withstand the corrosive effects of soil and moisture. The grounding electrode conductor should be securely attached to the ground rod using a clamp or other approved fitting. In addition to ground rods, other types of grounding electrodes can be used, such as metal underground water pipes, metal building frames, and concrete encased electrodes. If a metal underground water pipe is used as a grounding electrode, it must be supplemented by another type of grounding electrode, such as a ground rod. This is because plastic water pipes are increasingly being used, and a metal water pipe may be replaced with a plastic pipe in the future. Metal building frames can be used as grounding electrodes if they are effectively grounded. This typically involves connecting the grounding electrode conductor to the building steel at multiple locations. Concrete encased electrodes, also known as UFA grounds, consist of at least 20 feet of bare copper conductor encased in concrete. These electrodes are typically installed in the footings or foundation of a building. Concrete encased electrodes provide a very effective grounding electrode system due to the large surface area in contact with the earth. The selection of the appropriate grounding electrode system depends on several factors, including the soil conditions, the size of the building, and the type of electrical system. In areas with high soil resistivity, it may be necessary to use multiple grounding electrodes or to use ground-enhancing materials to improve the effectiveness of the grounding system. Ground-enhancing materials are substances that are designed to reduce the resistance of the soil around a grounding electrode. These materials typically consist of a mixture of minerals and chemicals that absorb moisture from the air and create a conductive path for fault currents. The grounding electrode system should be inspected and tested periodically to ensure that it is functioning properly. The resistance of the grounding electrode system should be measured using a ground resistance tester. The National Electrical Code does not specify a maximum acceptable resistance for a grounding electrode system, but a resistance of 25 ohms or less is generally considered acceptable. If the resistance is higher than 25 ohms, additional grounding electrodes may be required. In addition to measuring the resistance of the grounding electrode system, it is also important to visually inspect the grounding electrode system for any signs of damage or corrosion. Any damaged or corroded component should be replaced immediately. Proper grounding is essential for electrical safety and system reliability. By following the requirements of the National Electrical Code and using appropriate grounding techniques, it is possible to create a safe and effective grounding system for any building or structure. Furthermore, when considering bonding conductors, National Electrical Code Section 250.64e provides guidance on the installation of bonding jumpers. These jumpers are used to connect different grounding electrodes together to form a common grounding electrode system. The size of the bonding jumper is determined by National Electrical Code Table 250.66, based on the size of the largest grounding electrode conductor. The bonding jumper must be securely attached to each grounding electrode using listed connectors. The connectors must be suitable for the type of material being connected, such as copper to copper or copper to steel. In addition to bonding grounding electrodes together, it is also important to bond non-current carrying metal parts of electrical equipment together to form an effective ground fault current path. This is achieved by using equipment grounding conductors, which are typically run with the circuit conductors. The size of the equipment grounding conductor is determined by National Electrical Code Table 250.122, based on the size of the overcurrent protective device protecting the circuit. The equipment grounding conductor must be connected to the grounding terminal at each outlet and equipment location. When running equipment grounding conductors in metallic raceways, it is important to ensure that the raceways are properly bonded together. This is typically achieved by using bonding bushings or bonding lock nuts at each connection point. In addition to the requirements of the National Electrical Code, it is also important to follow any local codes or regulations that may apply. Local codes may have additional requirements for grounding and bonding. It is always best to consult with a qualified electrical engineer or electrician when designing and installing a grounding system. A qualified professional can ensure that the grounding system meets all applicable codes and regulations and that it provides a safe and effective ground fault current path. Proper grounding and bonding are essential for electrical safety and system reliability. By following the requirements of the National Electrical Code and using appropriate grounding and bonding techniques, it is possible to create a safe and effective electrical system for any building or structure. The importance of a low impedance ground fault current path cannot be overstated. A low impedance path allows fault currents to flow quickly and easily back to the source, causing the overcurrent protective device to trip and energize the circuit. This protects people and equipment from electrical shock and damage. A high impedance ground fault current path, on the other hand, can prevent the overcurrent protective device from tripping, even when a fault current is present. This can create a dangerous situation, as the fault current can flow through unintended paths such as the human body, causing electrical shock or even death. Therefore, it is essential to ensure that all grounding and bonding connections are tight and secure and that all grounding conductors are properly sized. Regular inspection and testing of the grounding system can help to identify and correct any potential problems. In summary, the grounding electrode system serves as the primary connection to the earth, providing a path for fault currents to dissipate. The equipment grounding system provides a path for fault currents to return to the source from non-current carrying metal parts of electrical equipment. Bonding ensures that all metal parts are electrically connected, creating a low impedance ground fault current path. By following these principles, a safe and effective electrical system can be created for any building or structure. This includes the consideration of 2 ground rods outside each of the 3 electric rooms, complying with National Electrical Code Section 250.52 and interconnecting the ground bars within these rooms using bare copper conductors enclosed in polyvinyl chloride conduit. This balanced approach ensures both safety and cost-effectiveness in establishing a robust grounding system.